Hello. A half-wave rectifier is often introduced as the simplest way to convert alternating current into direct current. But simplicity has a cost. In this lesson, we will quantify that cost in two ways. First, only 40.6% of the AC input power can become useful DC power even with an ideal diode. Second, the transformer utilization factor is only about 28.6%. By the end of this lesson, you will be able to derive both results and explain why they make the half-wave rectifier a poor choice for most transformer-based power supplies. Lesson objectives are: understand rectification efficiency, understand transformer utilization, derive the formulae for determining rectification efficiency and transformer utilization. Let us begin with the transformer's secondary voltage, which is sinusoidal. During the positive half cycle, the diode is forward biased and the current flows through the load. During the negative half cycle, the diode is reverse biased, so the current becomes zero. The output is therefore a train of positive half sine pulses. This pulsating DC has a central limitation. The load receives energy during only half of every electrical cycle. Rectification efficiency is the ratio of useful DC power delivered to the load to the AC power supplied to the rectifier. The DC output power is VDC times IDC, or IDC squared RL, where RL is the load resistance. The AC input power depends on the RMS current and the total series resistance, which includes the load resistance and the diode's forward resistance. It will also include the transformer secondary winding resistance, but to have calculations simpler, this is generally ignored. So we consider only the load resistance and the diode forward resistance. The diode resistance consumes power as heat, so it can only reduce practical efficiency. Let Im represent the peak current. For a half-wave rectified sine wave, the integration over a full half cycle or full cycle gives an average or DC current of Im divided by pi. The RMS current is Im divided by 2. These are not arbitrary constants. They come directly from the shape of the sine waveform of the voltage and current. We now substitute these two current ratios into the output power and input power expressions. Substituting the average and RMS currents into the efficiency ratio causes the peak current term to cancel. The result is 4 over pi squared multiplied by RL over RL plus RF. For an ideal diode, RF is 0 and the resistance ratio becomes 1. Therefore, the maximum theoretical efficiency is 4 over pi squared, approximately 0.406 or 40.6%. Any real diode resistance increases the denominator and pushes the efficiency lower. Imagine supplying 100 units of AC power. Even in the ideal case, only 40.6 units become the DC component that the load can use. The remainder appears mainly as ripple power with additional real losses in the diode and the winding resistances of the transformer. The RMS current still heats the circuit, but the average output is comparatively small. This is why the half-wave rectifier needs significant filtering and why its components are not used efficiently. Efficiency tells us how well electrical input power becomes DC output. Transformer utilization factor asks a different question. How much useful DC power do we obtain for each volt ampere of transformer secondary rating? The denominator is the transformer's RMS secondary voltage multiplied by its RMS secondary current. A low transformer utilization factor means that the transformer must be physically larger and more highly rated to produce a given DC output. For the transformer secondary, the RMS voltage is Vm divided by square root of 2. The RMS current is the same half wave value Im divided by 2. For an ideal load, the DC power can also be written as Vm Im divided by pi squared. Dividing that DC power by the transformer volt ampere rating gives 2 root 2 over pi squared, which is approximately 0.286. The practical interpretation is stark. A 100 VA transformer can support only about 28.6 watts of DC output in this ideal half-wave arrangement. The secondary winding carries an RMS current that contributes to heating and VA rating, yet the average DC result is small. In addition, the secondary current is unidirectional, so it introduces a DC component of magnetization that can push the transformer core towards saturation. And when the transformer core saturates, it will distort the waveforms and that will lead to additional heating. Now compare the transformer utilization factors. The half-wave circuit achieves about 0.286. A center-tapped full-wave rectifier, which you will study later, improves this to about 0.693. A bridge rectifier, which you will also study later, reaches about 0.812. In other words, the bridge extracts almost 3 times as much DC power per transformer VA as the half-wave circuit. This is a major reason full wave topologies dominate practical transformer based power supplies. We can now close the loop. The maximum ideal rectification efficiency is 40.6% and the transformer utilization factor is only 28.6%. Together with high ripple and possible core bias concerns, these values make the half-wave rectifier suitable for very low power, low cost applications. When transformer size, output power, or ripple performance matters, a full-wave rectifier is usually the better engineering choice. You may pause the video and review what you have learned so far. Thank you for watching.